Welcome back. This is the second half of the lecture 4.4, week 4 of the class Neuronal Dynamics. I will ask the question, where is the firing threshold? A question that we have already considered in the context of the Hodgkin-Huxley model in week 2, and also in the context of integrated file models in week 1. So, where is the firing threshold in one of these nonlinear two-dimensional neuron models that we consider this week? If you give a short current pulse, then you find that if the current pulse is strong enough, it evokes an action potential. If you reduce the amplitude slightly, you may still find an action potential. If you reduce it more, you may find that there is an action potential, but it's delayed. The question then is, can we understand this delayed spike initiation? Now, we have already seen in the first half of lecture 4.4 that bifurcations can help us to understand neuronal behavior, the difference between type 1 and type 2 neuron models, for example. In fact, the field of nonlinear dynamics, in particular bifurcations, applied to neuron modeling, has been a very lively field during the last 20 years, and there are many people who have made substantial contributions to that part of theoretical and mathematical neuroscience. I may name Nancy Koppel, Bart Ehrmantraut, John Rinzel, Eugen Izikevich, and some others like Boris Gutkin or David Hansel, and many others more. It's an active field that has been beautifully developed over the last years, and I would like to show in this second half of that lecture 4.4 how the kind of bifurcation analysis in 2 dimensions can help to understand thresholds in neuron models. So in the first half of this lecture, I have introduced the saddle node onto limit cycle bifurcation. This is a situation here where I have a W null line and a U null line, and they have 3 fixed points, one a stable one, then a saddle, and followed by an unstable one. The stable one, also called a node, will merge with a saddle when I apply a constant input current, and the 2 fixed points disappear. You have seen that in this case, if the 2 fixed points have disappeared, a limit cycle emerges, a limit cycle around the remaining unstable fixed point, and this limit cycle has a part where the trajectory moves incredibly slowly. And the reason is that it moves through the region where just before the bifurcation, there have been fixed points. The flow at the fixed point is, by definition, 0. Now, in this second half of the lecture 4.4, I would like to stay in a regime where there are still the 3 fixed points, a stable one, a saddle one, and an unstable one. And now I consider the situation that we give a pulse input. So suppose the neuron at the beginning is at rest. The voltage U is at the resting potential, U rest. And now I give my pulse current. As we have seen, a pulse current will lead to a horizontal jump of the trajectory to a new initial condition, say this initial condition here. Now, if we look at the arrows in this phase diagram, we would find that the movement is towards the U null line, where it turns around, and then it goes back, and it turns around, and it goes back to the stable fixed point. If I plot this over here, the pulse leads to a jump, and afterwards I have this big voltage trajectory followed by a downswing, and then I come back to the resting potential from below. Okay, now if I reduce the size of the pulse, then the jump will become smaller. If I reduce the size of the pulse even further, the jump may end up very close to the saddle point. Now at the saddle point, the flow is slow. trajectory will move. The trajectory will move very, very slowly. The size of the arrows is very small. And this leads to a situation that initially, from this new starting point, just a little bit below, the trajectory increases very, very slowly before it finally takes over, and we have basically the same kind of pulse as before, however, with a delay, delayed pulse initiation. So let's discuss this again. This is the saddle point. The saddle point is characterized by a flow pattern where in one direction there's a movement towards the threshold, towards the saddle point, whereas in other directions there's a movement away from the saddle point. So if a trajectory starts close to the saddle point, then it's first attracted towards the saddle before it moves out. Let's apply this to our situation at hand. The strong current pulse that I apply first leads to a jump to this new initial condition here, and we expect a movement back to the stable fixed point. Now, if I start at a situation that's closer to the saddle point, I might be attracted towards the saddle point first, very slowly. Here the movement is slow, before it moves out again. If I start on the left-hand side, then it will turn over as indicated over here. Thus, there's one unique trajectory. A saddle point is characterized by one unique trajectory. There's only one trajectory from below that will really approach the saddle and stay at the saddle. All other trajectories will either bend to the left or to the right. Therefore, this attractive manifold of the saddle, the stable manifold, will serve as a threshold for pulse input. I said there's only one trajectory coming from below. In fact, there's another one coming from above. So if we start close to this stable manifold that's attracted towards the saddle, then we can expect a slow movement and therefore delayed spike initiation. Now here's a situation coming from a real simulated model. Here is my U-null line. This one here is, so the dashed line, the blue dashed line is the W-null line. Here is my DUDT, the U-null line. And I have the three fixed points, a stable fixed point here, a saddle point over there, and an unstable fixed point over here. Now, if a trajectory starts to the right-hand side of this stable manifold, it makes the detour. If it starts to the left-hand side, it goes straight back. If I zoom in onto this region, I see the different arrows, and I can predict that if you start here, you still move towards the stable fixed point, towards the rest, while if you start here, just a little bit on the other side, it will move up here. And this is shown in these iterations here. We are now very close to this threshold, to the separatrix, and if you start just above, just on the right-hand side of the separatrix, the trajectory is first attracted towards the saddle. Remember, this is the saddle, and then it makes the large detour. This movement here is very slow, and this slow movement gives rise to the delayed spike initiation. Now notice that there is no shortcut possible, because there's another attractive trajectory starting from this unstable fixed point towards the saddle. So any trajectory starting on that side will have to make the detour to go back. Any trajectory starting on this side can go back directly. So this manifold, the stable manifold of the saddle point, plays the role of a threshold. This trajectory cannot be crossed. So what we have seen so far is that a system that has a saddle node onto the limit cycle bifurcation, and that's not yet at the bifurcation, will generate delayed spike output in response to short input pulses. However, some neuron models don't show this. If I reduce the amplitude of the pulse, the amplitude of the response is simply reduced. So let's go back to our Fizio-Nagumo model. The Fizio-Nagumo model has a W null line, which is a straight line, and we have a stable fixed point down here. Now, the Fizio-Nagumo model, upon application of a constant current, will show a Hopf bifurcation. The point moves, the fixed point moves, and at some point it becomes unstable. But let's go back to the situation where the fixed point is stable. And let's apply a pulse input. A pulse input will lead to a jump, a horizontal jump of the membrane potential. Then we follow the flow pattern, and what we see is that it will go back like this. So in response to the input pulse, I have an increase of the voltage, and then it goes down, it comes back from below. Now, if I reduce the size of the pulse, and I start here, well, all on this side, the flow is to the right and slightly to the left. And now a new trajectory can develop, which looks different. And this new trajectory will basically look like this. If I move over here, there's no reason that there shouldn't be a shortcut back to the fixed point. In this kind of model with a Hopf bifurcation in the regime where we have a stable fixed point, there's no such thing as a strict threshold. There's no stable manifold that could serve as a threshold. Shortcuts are possible. So here again, the situation, normally I make the detour, but there's no explicit threshold. If I start somewhere else, a shortcut might be possible. However, the dynamics of the variable W arises, if I come from the Hodgkin-Huxley model, from N, the gating variable N, and the gating variable H. Both of these variables are fairly slow compared, for example, to the M variable. Therefore, the dynamics of W is slow. Now let's take the limit where tau W, this time scale here, is much larger than the voltage time scale, tau U. Now this means that the change dW dt, I bring the tau to the other side, is G divided by tau. But tau is very, very big. Therefore, this is nearly zero. That means if I construct a typical flow arrow, which would have two components, it would have a component delta W, and it would have a component delta U, then normally the delta W is much smaller than the delta U, and that means that flow arrows are nearly horizontal. Wherever I am, flow arrows are nearly horizontal. Now there's one exception, and that is on the U node line. on the new node line, delta U is exactly 0. Therefore, the flow arrows must be vertical. But the amount delta W is very small. Therefore, I have a very slow, vertically upward. Now, the trajectory cannot get very far away from the U-node line, because if you're away from the U-node line, the nearly horizontal arrows will push you back onto the U-node line. So, if I start here, I apply a short current pulse. The short current pulse leads to a horizontal jump. Now I have a rapid rise, and then I have a very slow movement along the U-node line. If you are on the U-node line, you're pushed upward, but as soon as you are away, you are pushed leftward back towards the U-node line. So take some time when you go along the U-node line. If the upswing is phase 1, then this would be phase 2. And now suddenly there's no U-node line anymore that hinders your movement. So you move rapidly down, and then you come back slowly, very slowly, from below towards the resting potential. Now, in this case, if the movement is always nearly horizontal, if you start here, you will move rightward. If you start here, you will move leftward. So this is a leftward arrow. If you start here, you have a trajectory starting here, coming down. If you start here, you have a trajectory starting here and then coming down. If you start on the left-hand side of this branch, you will go down immediately. In other words, the middle branch of the U-node line, this is the U-node line, the middle branch of the U-node line acts effectively as a threshold for spike initiation under pulse input. Let's just make a little detour about this notion of separation of timescales. So we said that the timescale tau W is slow compared to that of the voltage variable U. So let's look at the ratio tau U over tau W. Now this is then a small number. It's unit free. Let's set it to epsilon, much smaller than 1. So in this regime down here, errors are nearly horizontal. There's a little component of size roughly epsilon upwards, but effectively they are horizontal. And as epsilon gets close to 0, they become more and more horizontal. Now on the U-node line, errors have to be vertical, but they are very small. And I argued that the trajectory is always pushed back towards the U-node line. In fact, you can show that if you zoom in, the distance between the trajectory and the U-node line is always of order epsilon. So as the separation of timescales becomes stronger and stronger, as epsilon goes to 0, the trajectory becomes slower and it gets closer to the U-node line. Once it's up here, it can jump, and it jumps with a fast timescale. So here's a simulation of the Fitz-Nagumo model under pulse input under the assumption of a separation of timescales. You see that while it moves along the U-node line, the movement is very slow. While it moves back to the resting potential, the movement is very slow. On the other hand, the downswing of the action potential is very, very fast. To summarize, the methods of phase plane analysis allow us to discuss delayed spike initiation under pulse input or other changes of spike initiation if we reduce the amplitude of the pulse. In a type 1 neuron model that's canonically characterized by a saddle node onto limit cycle bifurcation, delayed spike initiation is the norm. Now, for neurons, for example, with a Hopf bifurcation, the situation is different. They don't really have a threshold. Formally, amplitudes of the response can have any size. However, in the limit of a separation of timescale, the middle branch of the U-null line plays effectively the role of a threshold. Now, these are, as I said, classical topics of theoretical and mathematical neuroscience, of computational neuroscience, and I invite you to look at the literature and please also have a look at the quiz.